start the recording. All right, so now these examples that I'm doing, the book has good examples, but I sometimes try to do some additional different examples so you have a wider variety of examples to look at. So take a moment and copy this example down, and then we'll talk about finding this limit. Okay. So limits as t or x go to infinity are important. In particular, they're very important for like rational functions because, as you know, with rational functions, if those limits relate to horizontal asymptotes. How many recall that from pre-calculus? If you take the limit of a rational function as f of x as x goes to infinity, how many remember that would find you a horizontal asymptote? Yes, Nicholas remembers, Ian, Helen, absolutely. And it's important to be able to find limits as t or x go to infinity. In calculus, what you're going to be learning later on in chapter 4 is how to calculate. Thank you, Sebastian. You're going to be learning how to calculate limits. Well, what I'm trying to say is you're going to be learning how to graph some fairly complicated functions using calculus to help you graph the functions. You're going to be learning about things like concavity and increasing, where functions increase, decrease, anything to help you graph the function. So what we need to recognize here is that it's going to be hard to compute this limit unless we do what to the denominator? What do we have to do with those two factors in the denominator? Multiply. That's right. That's right, Nicholas. So let's proceed here. Okay, we're going to multiply these two binomials in the denominator using the FOIL process. So is everybody good up to this stage here? Excellent. All right. Well, of course, we're going to combine like terms. Thank you, everybody. Of course, we're going to combine like terms here. And so our limit now, and you notice I'm carrying the limit at each step of the way. That's using proper notation. That would be expected on your work for the exam. So when you do your homework, you should really, train yourself to use proper notation. All right, so our limit then is the limit as t approaches infinity of 4 times t to the fourth plus 5 over 2 times t to the fourth minus 5t squared plus 2. Now you all know that the dominating terms in the numerator and the denominator are the ones with the highest power. That's something that you learn in pre-calculus. And to help us figure out this limit, we can rewrite the rational function. We can rewrite it by multiplying through the numerator and denominator by 1 over t to the fourth. As you see here. We're not changing the expression because 1 over t to the fourth times 1 over t to the fourth is equal to 1. I mean, we're rewriting the expression, but mathematically it's the same limit. Okay, and so we can rewrite the limit this way. How many recall doing this kind of process maybe in pre-calculus? All right, well, you might have seen it. Okay, so Nicholas and Lynn don't remember this. Okay, well that's good, because then you're learning something new here. Anna says kind of remember, but not really. Okay, now what I'm going to do, I'm going to circle the limit, and I got the limit written as the way the 1 is there. And then 2 is the limit written this way. Which way is it easier to determine the limit? The way it's written in 1 or the way it's written in 2? Well, so 3 folks said in 1, but let me ask you this. As t goes to infinity, what's 5 over t to the fourth going to go to? What does this have to go to as t goes to infinity? Rodrigo likes 2. I mean, what does it have to go to? Has to go to 0. Has to. Okay. What about 2 over t to the fourth? What's that going to approach as t goes to infinity? That's going to go to 0. So, in our minds, we're saying, okay, those terms drop out. And this term here, 5t squared over t to the fourth, that would approach 0. Because we simplify that, that's just going to be 5 over t squared. So the goal in multiplying the numerator and denominator by the 1 over t to the fourth is so we could rewrite the rational function in this form here, and that makes it easy to compute the limit. All right, are there any questions on that? All right, well then let's proceed over to the next page. So now our limit, all I've done was I just, simplified the, on the previous page, the, 4 4t to the fourth over t to the fourth is just 4. And then 2 to the t to the fourth over t to the fourth is 2. Okay, and so I just simplify that. And now we're able to take the limit. And these terms here, these three terms go to 0 in the limit. So now that I've taken the limit, I don't have the limit here anymore, right? The limit's not here anymore because I took the limit. And the limit of the rational function as t approaches infinity will equal 4 plus 0 over 2 minus 0 plus 0. Hence, you get 2. And what this means, practically speaking, is that the function f of t equals 4t to the fourth plus 5 over t squared over the denominator t squared minus 2 times t, 2t squared minus 1. That's going to have a horizontal asymptote at y equals 2. That, this is, of course, where it's understanding that we're letting f of t here, f of t is going to equal y, right? So, all right, let me give you a moment to copy that down. All right, are there any questions at all? Are there any questions at all up to this step here? All right, well, I think it's important to put this problem in context of what you learned in pre-calculus, because now there are horizontal asymptotes, and what other kinds of asymptotes are there? What other? Vertical and diagonal. That's right. You can have oblique asymptotes and vertical asymptotes. That's right. So here we could ask, what are the vertical asymptotes of this function? What are the vertical asymptotes? Well, okay, Nicholas is on the right track. We have to find the vertical asymptotes. How do we find the vertical asymptotes? And this is assuming there's no simplification between the numerator and the denominator, and there's not in this problem. Ian's right. We have to make the denominator 0 and solve for t. Okay, so let's do that. The function f of t is going to have vertical asymptotes when either t squared minus 2 equals 0 or 2t squared minus 1 equals 0. And so you solve for both of those little equations, and you'll find that you're going to get t equals plus or minus root 2 and t equals plus or minus 1 over root 2. The reason I'm going over the vertical asymptote part is because in your homework for section 2.6, you do have questions, at least a few, that ask you about vertical asymptotes. So, um, and it's important. It's always important. It's a good review. Are there any questions so far? All right. Okay, excellent. So our function has vertical asymptotes. It has 4 vertical asymptotes. And this function, if you were to graph it, it's a difficult function, really, using the TI-84 calculator, 83 calculator, to graph, because it's just you almost have to zoom in on certain parts of the function to corroborate this behavior. But I did do that. So now we know what vertical asymptotes the function has. Okay, are there any questions? Any questions? So far? All right. Excellent, Layla. All right, so I wanted to kind of make another comment since we're talking about rational functions. So I'll move to the next page if everybody has this copied down well. All right. So note that this function differs from a function like g of t equals t minus 2 over t squared minus 4. Okay. What's the difference here? What's the difference? Well, and I'm just gonna, I'm sort of like I'm lecturing it out to you because you've seen it before. The denominator here in this g of t is t squared minus 4. And that's going to be undefined at t equals 2 and negative 2. But it only has one vertical asymptote. It doesn't have 2 vertical asymptotes. It has just one. It's okay. The problem that we did before, this our f of t function, the denominator gave us 4 vertical asymptotes. Okay, but in other words, the denominator, if we were to factor that denominator out in the f of t function, we'd have 4 factors. Even though for the g of t function we have 2 factors, t squared minus 4 factors into t minus 2 and t plus 2, we still only have one vertical asymptote at t equals negative 2. Because the factors t minus 2 simplify out. And so g of t will equal 1 over t plus 2. But t is not allowed to be negative 2 or 2. And at t equals negative 2, you have the asymptote. And at t equals 2, you have the hole in the graph. There's a hole in the graph. Right? Like it's a removable discontinuity, so to speak. Well, that's what it is, actually, at t equals 2. Let me stop and let you copy here. Okay, are there any questions at all with this? And I'll just mention the reason I wanted to talk about this function GT is whenever I think about rational functions, I always think about the case where, a factor in the numerator and the denominator simplify out. And then, okay, what happens there? And so I thought it was how many find that to be a nice little, just a little review, this little part here. Kind of nice to see it again. Excellent, Nicholas, thank you. All right, are there any questions at all before we move to our next limit problem? All right, well then, let's move on. Thank you, Shako. Okay. Here's another limit we're going to determine. Okay, so we want the limit as x approaches infinity of the square root of 9x squared plus x minus 3x. Now, of course, we could graph this function, square root of 9x squared plus x. And I do need a parenthesis here. Sure to hold on here. Sure to fill that in. Okay. Well, Nicholas, we can't combine it. It would be lovely if we could combine the 3x and the x, but the problem is that the x here is under the square root, and the 3x is just like apart from the square root. There's no connection between the two. So no, we can't combine. We can't combine those. That's all right. That's all right. I like questions being asked. This is clearly a kind of a difficult situation, but didn't we see, well, factoring out the x, well, there's going to be an x involved, Trevor, but I like Lynn's idea about taking the conjugate. What would the conjugate be of the square root of 9 squared? What's the conjugate of the square root of 9x squared plus x minus 3x? That's right, Ian. That's right, Lynn. It's the same, but you have a plus 3x. So that's what we're going to do. Let's go to the solution. We're going to multiply by the conjugate. On the numerator, we're going to multiply, and of course this square root of 9x squared plus x, or square root of the quantity 9x squared plus x minus 3x, that's over 1. We know that. So I'll multiply the numerator and denominator by the conjugate. And this allows me to rewrite this in a simpler form. We want to remove the square root. We want to remove the square roots. We'll use FOIL, by the way, to multiply the binomial the two binomials in the numerator, and we get to this step here. Okay, give you a moment to catch up here. I'm correcting this on my notes, this problem with the parentheses there. Okay, and this is the kind of work I would want to see on the exam for this kind of problem. Okay. Are there any questions to this third step here? All right, thank you, Anna. Do some nice things happen? Do some nice things happen here? Sure. What happens, Nicholas? What happens to these two terms? They cancel out. And then okay, ditch the square root. Okay, the radical's removed. So, right, you have 9x squared plus x. And so then, your limit becomes this. Becomes this now. You notice I'm carrying the limit every step of the way. And then even more nice things happen. Yeah, the 9x squareds cancel out, and only the x is left. Extend this over a little bit there. Okay, so take a moment, write that down. Square root should be over here. Well, certainly this is better than what we had. You know, down to this step here. It's better than what we had, but we're still not you know, we're still not quite where we need to be in terms of this limit. We have to simplify things a little bit more. Okay, we have to simplify things a little bit more. So what's the hardest part of the limit as x goes to infinity of x over that denominator? What's the hardest part to deal with of the three different terms that you see? That's root, that's square root, that's right. So what I'm going to do is I'm going to try to rewrite this fraction in a different way. What we're going to do is we're going to multiply by 1 over x on the top and the bottom. And this relates to what, in a way, to what Trevor was talking about in terms of factoring. Although we're not exactly factoring, but it leans towards that direction. So of course, I'm multiplying by 1 over x on the numerator and denominator, so I'm just rewriting the limit. Yes, Rodrigo, let me go back one page. Hold on, everybody. Let me see here, one moment. Question, Rodrigo, on that? Okay. This, by the way, all right, good. And this goes all the way, right? That fraction there. Okay, you're welcome. So I'm going to multiply by 1 over x on the numerator and the denominator. And of course, in the denominator, the 1 over x has to be distributed to both the square root term and the 3x term. But when I distribute 1 over x to the square root term, I'm going to write 1 over x as the square root of 1 over x squared. And the reason I want to do that, is because then, well, you know, you have a rule that says the square root of a times the square root of b is equal to the square root of a times b. So the 1 over x squared multiplies the 9x squared and the x to give me this expression under the radical sign. And that is going to make the problem amazingly easy for us. But are there any questions so far? All right. Well, yes, Sebastian has a good question. 1 over x is equal to the square root of 1 over x squared. The square root of 1 over x squared, you can think of that as 1 over x squared as 1 over x times 1 over x. So the square root of 1 over x squared is the 1 over x. All right, are you comfortable, Sebastian? Okay, good, good. All right, well, we'll do a little more, we'll work a little bit longer on this. So we're almost there. I'm going to simplify what's under the radical. And now this limit, it's easy to take the limit. It's easy. I mean, let's see, step 4, I have an, let me see, 1 over x. Nicholas says on step 4 should be 1 over x, not 1 over x squared. Oh, yes, thank you. This here, this, well done. So class, x over x squared is 1 over x. Yes. And now when you take the limit, I'll put in a little extra step here. You're going to get 1 over the square root of 9 plus 0 plus 3, and that's going to get us 1 over the square root of 9 plus 3, which is going to be 1/6. Let's see. Trevor says, why is it plus 0 again? Well, as x goes to infinity, what would 1 over infinity be equal to in the 1 over x? 0. That's why after I take the limit, I can just put a 0 there. We're really using the limit laws they talk about in the book that you learned from section 2.3. We're just doing them in our head when we work it out, but it's fine. Trevor, you're good? Excellent, excellent. Okay. Now, of course, this function, I mean, you know, if you were to graphically try to verify this result, that the limit is equal to a 6th, you know, you might have to, you know, graph the function and go out to, you know, x equals 1,000 or 10,000 to finally come upon this. You can graphically verify these results by looking at the function and, you know, going out and, like, you know, in the function to a very large x value. But, you know, we want to do it mathematically if we can. All right, are there any questions before we move on to the next example? All right, very good. Well, we will move on. All right, take a moment to copy this down. All right, so an interesting problem. And it's not one that right now we want to find the limit as x goes to infinity of the quantity 1 minus 2 over x raised to the x power. And this problem is not one right now that you can mathematically find using the limit laws. In order to mathematically find this limit, you need to learn a limit theorem called L'Hopital's rule. You'll see that in calculus 2. You'll see this problem again in calculus 2. But right now, what we need to do is use our calculator to help us approximate the answer. So what I'll do is let me bring up the calculator here, one moment. I can find it. Here it is. All right, and let me see here. Let me go to sharing, share application. Let's see, this is what I want. Okay, give me one moment here. Hold on. Okay, let me just bring it back. Sorry. Good. Okay. All right. So what I want to do is I want to, well, first of all, in my mode here, yeah, everything's good. Everything's good. You'll notice, well, all right. So I'm going to type in the function 1 minus 2 divided by x. Hold on here. 1 minus 2 divided by x. I don't know why it's acting up here. Let's try this again. Okay, and raise that to the x power. Now hold on, I saw a thing come up here. Yeah, so Lynn, the float, yeah, this under mode, so float is floating decimals. I am, to be honest, I'm not exactly sure what that means. I think it means how many decimals it'll give me. I'll tell you what, we'll get back to that, okay? We'll get back to that. We won't worry about that just yet. But what we're going to do here is we have our function in here, and we're going to use something called table set. Okay, so table set is above window. So since table set's in blue, I have to hit the blue button to get it. So I go second window to get the table set. Now the table start, what I need to do, remember, I'm looking at this function, the quantity 1 minus 2 over x raised to the x power, and I'm letting x get very large. So I want to examine what this function approaches as x gets large. So maybe I'll start my table at 100 for my table start, and I'll skip by 100. And then I'll go to auto. I'll do auto on both. So see, when you have a table, you set it up in your TI 8384 calculator, there are different features. You can, so the independent variable, I'm putting it on auto. And that means that the table is going to start at 100, but then it's going to, the delta table is 100. So it's going to go 100, 200, 300, 400, 500, and so forth, because the change in value is going to be 100. The dependent variable, which is the value of my function 1 minus 2 over x to the x power, that's on auto. So that, of course, I usually want to be on auto. So what we'll do now is we'll look at the table. The table is in blue above graph. So if I go second graph, it produces a table. Okay, and you can see it's starting to produce values. Okay, so table is something that you should have seen in your pre-calculus. I've taught pre-calculus at Montgomery College, so I know we teach it in there. But if for any of you the table feature in the calculator is new, well now you've seen it. Okay, so the Actual value that we're going to want to get is 0.1353. Okay. And so if we let x get bigger and bigger and bigger, we'll see that 0.1353, it stays pretty consistent. And so that's going to be our answer. The answer is going to be 0.1353. That is the limit of 1 minus 2 over x to the x power as x goes to infinity. That's the limit correct with 4 decimal places. I can always go back to table set, by the way, and I can start the table at 10,000 and then have a delta table by 1,000. You know, I can adjust the table and look at the table set. Look at the table, and you can see it's not going to change. It's not changing. So that's how you do that. The float feature on the calculator, I'll have to get back to you on that. I'm not exactly sure what that means. Let me just check one thing. Right, so I'm back. I hit the wrong button. Sorry about that. One moment here. Okay, so I just went into Google. So it says floating on decimal mode displays up to 10 digits. You can select the number of digits 0 through 9 to display to the right of the decimal for decimal answers. So that's what I thought what floating meant. But hold on, let me see here. There might be a. All right, we're good on that. Wait, hold on. Nicholas says, yes, I understand. Yep. I hear you on that, Nicholas, and you're welcome, Lynn. All right, well let's continue on here. So now you see how to use your table feature on your calculator. And I want to do one more with you from section 2.5. Yeah. All right. Take a moment to copy this example down. So let me just see here. Right, 0.1353 Kelvin was the answer for the, wait, hold on. Yeah, 0.1353 was the answer for the last question. That's right. So, okay, now we want to find the limit as x approaches pi from the right. Notice that plus there, that's approaching pi from the right of the cotangent of x. So what might be a nice way to solve this problem? Well, we could do an expansion into sine and cosine, but all I really want to do is determine the limit. This one I don't want to do mathematically. I want to do it another way. We've seen mathematically that we can solve some limits. We've seen you can use a table to solve some limits. And now we're looking at the limit as x approaches pi from the right. From the right, that's what that plus means, of the cotangent of x. Sorry if I misspoke earlier. What's the one approach we haven't done yet? Graphically, that's right. That's right. We can look at a graph. So what we're going to do here is we're going to graph the cotangent. But the cotangent of x is equal to 1 over what? Think of your trig days. 1 over the tangent. That's right. So oftentimes these kind of problems, it's helpful to work with a function. I mean, I'm sure you know more about the tangent than the cotangent. You probably have the tangent of the tangent graph memorized. So what we're going to do is we're going to graph the tangent, and then from there we'll graph the cotangent. Okay, so here's the tangent. All right, and I guess let me just talk about it first, and then I'll let you copy it down. Okay, I'll let you talk about. I'll talk about it first. So the tangent of x, and if you put your calculator in Zoom Trig, you'll get a nice window, nice values. But we recognize this as the tangent function. The tangent is a cyclical function, and it has a period of pi. And I've drawn two cycles of the tangent function. And of course, we're interested in how the tangent behaves around pi. So the cotangent, since the cotangent is 1 over the tangent, all I need to do is look at the tangent to help me graph the cotangent. Okay, remember the cotangent of x is 1 over the tangent of x. So, like for instance, where the tangent of x equals infinity, the cotangent of x would equal what? Where the tangent of x goes to infinity, what would the cotangent of x equal? Well, right. Well, what's 1 over infinity? What's 1 divided by a huge number going to equal? That's right. It's going to go to 0. That's right, Ian. That's right, Nicholas. It's going to go to 0. So you notice that as the tangent function, when x approaches pi over 2, the tangent function goes to infinity. Well, that means the cotangent of function is going to go to 0. On the other hand, though, here, if we concentrate on this part of the tangent function here to the left of pi, okay, the tangent function is negative, okay, between pi over 2 and pi. Well, that means the cotangent would also be negative from pi over 2 to pi because the cotangent's 1 over the tangent. But as you approach pi, as x approaches pi, the tangent function approaches 0 right here, right? Well, that means the cotangent would have to approach negative infinity. Okay, similarly, if we look to the right of the tangent function at pi, the tangent function to the right of pi, okay, over here, okay, right there, the tangent to the function to the right of x equals pi is positive. Okay, but again, as x approaches pi from the right, as we approach pi from the right, the tangent function gets smaller and approaches 0. Well, 1 over a very small number is going to be close to infinity. 1 over 0 is infinity. And so the cotangent function has to therefore approach infinity as x approaches pi from the right. Okay? And that was the original problem. They wanted to know what was the limit as x approaches pi from the right of the cotangent of x, and the answer is going to be equal to infinity. But let me give you a chance to copy the graphs down. Okay. Are there any questions? All right, Nicholas is good. Leila's good. Yeah, John, on the exam, you would need to, if you had a question like this, you have to justify your answer. And for this kind of problem, you would need a graph to justify it. I guess you could, I guess you could use the table feature on your calculator and have values that are smaller than pi and greater than pi and look from both sides what the values approach. I guess you could do that too. All right. So generally, when you have your, generally your standard functions in trigonometry are the sine, cosine, and the tangent. I mean, those are your standard functions. And if you know the graphs of those functions, you can graph your other trig functions, the reciprocal ones, the cosecant, the secant, and the cotangent. We don't always need to get out our graphing calculator to graph something, right? All right, so are there any questions before we move on? right, Ian's good. All right, may I go to the next page? All right, Kelvin's good. All right, well then, this is our answer then. This is our answer. The limit as x approaches pi from the right, the cotangent of x equals infinity. And you'll have problems in WebAssign like this, but you know, maybe you only, like it's either infinity or negative infinity, and you have one chance to get the answer right. So you want to, you know, you want to take your time and get a graph. All right, so what I want to do, I want to talk about section 2.6. That is the section now on derivatives. Yay, derivatives, rates of change. But I want to give you a little class time to work on section 2.5. So let me stop.